Hello my friends, this is current and resistance lecture. This is mainly aimed at understanding current resistance, overall how simple circuits works and so on. And we start initially working on a very important law, Ohm's law as well. So how do we model a current? We learned about capacitors and how if we connect a capacitor to a battery or another power source, its plates charges. This figure is showing that. And if after a while I disconnect my capacitor from the power source and connect it to another thing or connect them by a wire, there will be a current going from one to the other plate. There will be actually electrons moving back here, combining with the protons, and the capacitor will be overall discharged. Along this motion, if I add a circuit element like a light bulb, these electrons will be passing through it and causing it to light up, as we've seen in a FET simulation. The wire heats up because of the motion of those electrons, and because they don't just move across, they hit the other atoms and other particles inside, and they make them jiggle more, so we have heat in wire. We didn't get to here yet, we will in the next section, but if we put a compass under a wire where electrons are moving, they are actually generating a current. We will see the compass needle is deflected because actually if there's a current, there's a magnetic field. We'll get to that in a bit. So those electrons that are moving are actually generating what we call a current. So moving charges. So if we have moving charges, we have current. Most often the moving charges are electrons, but sometimes they could be also protons, positive charges, ions simply. But conventionally we will take the direction of positive charges as the current direction. We'll get to that in a bit more, but if my electrons are moving in this direction, current is in the other direction. That's the conventional direction of current. Alright, as I stated in the reason for why the wire is heated, electrons as they move, they just don't go along a straight path. They hit the other atoms inside the conductor they are moving, as we see in here, jump here and there. Overall, they move in one direction. If the electric field is to the left, we learned that the electrons are pushed in the opposite direction, so the electric force on the electrons are in the opposite direction. So overall electrons will be moving to the right if the electric field is to the left. Here it is the same thing shown for a capacitor. We have plus, minus plates, and electrons moves. These green ones are showing the electrons moves opposite direction to electric field. Over here we have electric field in this direction to the right, here and down and so on, from plus to minus or high potential, not low potential as always. So electrons moves in this direction, but if we want to consider current again, current will be in that direction here. So conventional current is always in the same direction as the electric field. Again, electrons are moving in this case. We have a conductor, mainly electrons are free, but if we assume positive charges are moving in the opposite direction, everything works the same and this is our conventional current. This is how it is accepted to be conventionally. This is again showing the flow of electrons. I'm going to show the direction of current in this diagram, which is actually a simple circuit. This looks like pretty much similar to if we run water through a turbine. The water will go and rotate the turbine. And we have one important rule that we want to mention is the law of conservation of current. If the current is generated by particles, electrons or ions, they cannot be destroyed or created. So whatever goes in to an object in my system, it should be coming out. So electrons in are equal to electrons out. This is called the conservation of current. Current is generated by electrons, so if the electrons cannot be destroyed or created, they are conserved. Electrons are conserved, current is conserved. A wire carries a current. If both the wire diameter and the electron drift speed are doubled. Forgot to mention here that the speed, overall speed electron goes here as they jump between atoms to atoms is called drift speed. Overall, electrons goes in this direction, right in this figure, and they have a drift speed, drifting to the right. Now this question is talking about drift speed. So we have a wire. Let's visualize that, exaggerating the thickness of a wire to help us. Some electrons are moving through it. Let's say they're going overall in this direction. They are hitting the other atoms and so on, but overall they have a drift speed. We can call it drift if we like, in this direction. Now, and then they generate a current. Again, we take the direction of the current to be opposite to the direction of electrons. So overall, we'll have a current in this direction. If both the wire diameter and the electron drift speed are doubled. If I double the drift speed, there will be more charges moving around. Use the same color here, blue. So I am doubling the diameter. I'll have a larger diameter wire. And we will agree that more electrons can now move. Electrons can easily move because they have more space to go, so they will hit less particles. So overall, at a given time, from a section, more electrons will be passing. So more electrons pass from a cross section at a given time. If I increase the diameter, the area will increase. They will have more space to move. So it will be like a flow of water. If we increase the size of the diameter of the hose, there will be more water flowing in. So it will be easier flow for them. More flow, more current. So current will be increased. Current is directly proportional to actually the cross-section area. If I double the diameter, I double the radius, and the cross-section area is pi r squared. A is equal to pi r squared. So double R, if R doubled, current becomes 4 times. If I increase the drift speed as well, if we drift doubles, Current is also directly proportional to drift speed. That means more number of electrons per unit time or at a given time are passing through a section I'm looking at. So current will also double. So our current is doubled by the drift speed, doubled here, so 2 times current, and 4 times here, quadrupled if you like. We have quadrupled, spelling mistake here. Let me put 4 times. So 4 times larger, quadrupled. When you combine these, we have 4 times 2, 8 times larger. So your current becomes 8 times larger. Doubles due to their speed, and quadruples due to increase in cross-section area. And here is your answer. This example is asking us which bulb is the brightest. Brightness depends on how much current is passing through something, light bulb or any other object in a system. So we have current passing here, coming to the second light bulb, keep going. So whatever current comes in here goes into the other one. And they are here, we have identical light bulbs. So whatever resistance this wire has here, this wire will have the same resistance or same properties. Same resistance, same current. We'll get to this later on, but power is telling us how bright a bulb is, light bulb is, and it's equal to I squared R. I'm going ahead here, we'll get to this later on. So same resistance, same current, same power, same brightness. This is actually also preparing us for what we call a series circuit, when we put 2 objects in line with each other. Let's define current a little bit descriptive or quantitative. Current is described as the charge, number of charges passing through a cross-section area per unit time. So charges per unit time across a cross-section area. This figure nicely shows it. And when I put this in the mathematical equations, if I look at the total charges passing through a cross-section area and divide it by time it takes for them to pass, that's the definition of my current, charge per unit time, I'll find my current. Simple as that. If I know my current and time, I can also find the total number of charges passing through a cross-section area. This question here says every minute 120 coulomb of charge flow through this cross-section area of wire. So this is my cross-section area A. Every minute, so delta T is 1 minute, or 60 seconds. SI unit is seconds. Remember, we always go to SI unit. And number of charges that are passing through is the amount of charges that are passing through is 120 coulomb. What is the current in the wire? Let's assume it's going in this direction. To visualize this a bit better, this is because charges are moving. And we'll go with the general equation. I is equal to, sorry, let's go back. Current is equal to charge per unit time, and we'll find our current using that. charge is 120 coulomb divided by time 60 seconds. Total current through the wire is 2 coulomb per second, and the unit is called ampere or amps. Use capital A for that. So the answer is 2 ampere. A very similar question here. I'll quickly pass. The solution is already here, as you can see. It's a 100-watt light bulb. This is the power of a light bulb. Again, we'll get to this later on. Carries a current of 0.83 ampere. So I have a light bulb. Let's visualize this a little bit. It has a power 100 watts, and it carries a current 0.83 amperes. There's some wires inside this light bulb as always, and a current is passing through it to light it up, right? How much charge flows through the bulb in 1 minute? So the time delta T is 1 minute, again 60 seconds. This time I'm asked to find what is the charge. Starting from I is equal to Q over delta T. I can solve for Q easily, cross multiplication here, as I delta T, and here is the solution. As you work through this, you'll find it's 50 coulomb. We could also find how many electrons moves across this cross-section area to generate this current, or create this amount of charges. Knowing that one electron has 1.6 times 10 to minus 19 coulomb of charge. This is negative actually, but we're looking at the number of electrons, so regardless of the charge, we will look at the absolute value of the result. Simply, I can find this. If one electron has this much charge in coulomb, how many electrons would have 50 coulomb? Simply dividing by charge by the electrons. And again, taking the absolute value will give us how many electrons would generate this current, or how many electrons in total would have this amount of charge. And we will find 5 times 10 to 18 electrons. Another similar question. The discharge of the electric eel can transfer a charge of 2 millicoulomb. So my charge is 2 millicoulomb in a time of 2 milliseconds. So delta T is 2 milliseconds. This would be 2 times 10 to minus 3 seconds, and this would be 2 times 10 to minus 3 coulomb. What current in ampere does this correspond to? We use I is equal to Q over delta T. 1 ampere. Then we divide those numbers. A, B identical light bulbs connected to a battery which is brighter. If same current is passing through identical light bulbs, they will have the same brightness, and same current is passing through here because current has only one way to go. And as we discussed earlier, this is actually a series circuit. We'll talk about more in the future. So they are equally bright because they have the same current, same resistance, same power, same brightness. Since in electrons should be out electrons, we said, or charge is conserved. It's a conserved quantity. Charges generate current, so current is also conserved. This brings us to something what we call junction rule. If the current is conserved and my current enters into a junction similar to this figure over here, it will be divided into 2, 3 or 4 depending on what type of junction it's going into. And since the current is conserved, the in current, let's call this I1, should be always equal to odd current. Let's call this I2 and I3. So we say total I in, I'll just call it I in, should be equal to total I out. We add all the incoming currents and equate them to all outgoing currents. That's called junction rule, and it's because of the charge conservation or conservation of charge or conservation of currents. Over here in the second case we have 2 currents in, let's call them I1, I2 in this case, and I3 comes out, then we will say I1 plus I2 in currents are equal to I3 out current. There are several questions here about this in and out current. This question over here, for example, is asking us how do we compare the currents. We know here 2 ampere. We don't know these two guys. We know 3 ampere. So what I need to do here is to apply junction rule here at junction 1 and here at junction 2 to see how I can get information to compare these currents. In junction 1, when I apply I in is equal to I out, I have only one incoming current, that's IA, so I write that down, and I have 2 outgoing currents, that's 2 ampere and IB. So IA is equal to 2 ampere plus IB. Now that clearly tells me IA, the current A, is equal to IB, the current B plus 2, so A is larger than B definitely. Going to junction 2 and applying the same rule, so I in is equal to I out. In is 3 ampere this case, and out is IB. Sorry, don't go back. In is not only 3 ampere, we have 3 ampere in, and IB in, C over here, and we have IC out. So 3 ampere plus IB is equal to IC. Now IC is also bigger than IB, definitely, right? Because it's IB plus 3. And comparing A to C, I can see IC is bigger than IA. Current A is smaller than current C, because current A is equal to 2 plus current B, and current C is equal to 3 plus current B. Putting that into 1, we will have C being the largest, then comes A, and then comes B, where B is smaller than A, is smaller than C. Which version we have? E is C is larger than B. No, not that. This option here is our correct answer. C is larger than A and A is larger than B. Alright. So this is current. It is our answer. Attempt this question. Similar idea. In current is equal to out current. Find that unknown current. Is it in? Is it out? And what is the value? IDI is I in is equal to I out, and it should be 2 ampere to the left, so it should be an incoming current. And this question is solved. We have incoming 3 ampere to this junction here, outgoing 2, 3 amperes, 2 ampere, incoming 4 more ampere here, outgoing 6. Again, what is this guy? You will add all the ins, you'll get 7 ampere, incoming 3, incoming 4, 7 ampere. You add all outs, you'll have outgoing 6, outgoing 2, 8 ampere. Whichever is missing some, that's your answer. 7 is smaller than 8 ampere, so the one here should be incoming 1 ampere to complete and make I in is equal to I out. As we talked about how electrons, as they move, they hit atoms, what type of material will change the number of atoms we have in here. This is a conductor here. So as we try to generate a current, electrons tries to move. As they move, they hit particles inside the conductor they're trying to move in, and that creates a resistance against the current we are trying to generate. Remembering that it will be in the opposite direction of the electron motion. That resistance depends on how thick our wire is, or cross-section area. We cannot touch base on that with a question. That depends on how long our conductor is. It also depends on the type of the conductor, how large are the atoms the electrons will be hitting, or how close they are to each other, and so on, which is defined as resistivity. So resistance of a certain wire can be defined, and we will use the R symbol for resistance as equal to rho L over A. Here, as I've defined here, L is the length, as you see in the picture. A is the cross-section area. And rho is the resistivity. Depends on which type of material we are using. So the resistance depends on the geometry of the wire, how long and how thick it is, and also what it is made of. This table here from our book is listing several conductors and how their resistivity changes. As we see, copper has quite low resistivity, which is something we use for as a wire in our power systems. We can easily compare resistances using the lengths, cross-section areas, and type of materials. For example, this question is talking about 2 wires made of the same material, but wire 2 is twice the length of wire 1. So if this is L, this is 2L, and twice the diameter. So I'm gonna go to radius directly. If twice the diameter, twice the radius, so this is 2R, this is R then. What is R2 over R1? If I calculate the areas, cross-section areas, A2 will be pi times 2R squared, not pi, 2R squared, so 4 pi R squared, and A1 will be pi R squared, We already know one length is L and the other is 2L. They are the same material, so they have the same resistivity. And if I call this one A, this will be 4A. And writing down the resistances here, then R2 will be rho 2L over 4A, and R1 will be rho L over A. I can cancel what I can cancel, and I'll have R2 over R1 to be equal to 2 over 4, divide each by 2, we'll have 1 over 2. And that's our answer. So we can easily solve, compare for the resistances, knowing the resistivity, length, and areas of wires. Another important fact in a circuit, in a system where we're trying to generate a current and make the devices work like a light bulb, we use power source. And batteries are a very common power sources. What happens inside a power source is that, unlike capacitors, the electrons don't come from one side and stop on the other side. Well, this is plus, this is minus. If I go the electron-wise, electrons would go in this direction. They don't come and stop here. They are pushed inside the battery, across. And this pushing is maintained by what we call electromotive force. Or short for EMF. Without going into too much details, there is a force pushing electrons across, so it keeps going a longer time. There's actually chemical substances inside here maintaining the work of the battery. Without going into too much detail, electrons are pushed across, current keeps going, and of course conventional current will be in the other direction. If I have plus here, minus there, I'll have current in this direction while the electrons are going in that direction. And that's what's called battery, and that's what is electromotive forces, and we use epsilon to symbolize this electromotive force. Again, it's called either EMF or electromotive force. So we use batteries in this fashion to build circuits and make things work. They maintain the motion of the particles, charges, and thus a current, which does a work for us, and so on. I'm gonna go quickly a little bit here. These are logical questions, conceptual questions on a battery connected to a wire, creates a current. What changes, increases the current? Thinking in terms of how many charges moves and so on. So if we read this through, it will be keeping the wire the same length but making it thicker. Electrons will be easier. More particles will be going from a cross-section area in a certain amount of time. That's more current. If we add batteries in this fashion, what we do is to add their epsilons to, this is called epsilon. Epsilons to find the total potential difference across. So 3 epsilon in this case, 3 times 1.5 volt. The reason electrons are pushed in a circuit when we connect these from plus to minus is that we have electric field, as we have seen initially. Again, electrons are pushed in this direction, but I'm going to drop the motion of electrons and I'm going to draw current. Positive charges would move in this direction, in the same direction as electric field, and they generate a current. It's because there is a potential difference. We have high potential here, low potential there. Generally take this side as 0 volt. This side would be, in this case, 4.5 volt plus charges will be moving, generating that current. This is E, I'll show here, and that is I actually. Doesn't matter, E and I, current and electric field are in the same direction, but let's keep the convention here. So this electric field pushes positive charges. We have current from positive to negative because we have a potential difference, which is 4.5 volts here, and we have electric field directed from high potential to low potential. This part I'm gonna skip. I don't know how doable it is. We don't really have earphones with a cable, but if you had to, go ahead and try it. Put in a set of earphones from a portable music player and place the plug on the table. Moisten your fingertips and hold a penny in one hand and a paper clip in the other. This makes a very weak battery. The penny and the clip are the electrodes, and your moist skin is the electrolyte, kind of a chemical that is needed for batteries. Is your body. Touch the paper clip to the innermost contact of the headphone plug and the penny to the outermost. You will hear a very soft click as the potential difference causes a small current in the headphones. If you have the earphones, go ahead and try this. Current, potential, and resistance relation is actually Ohm's law. Ohm's law will keep coming up in next chapter as well. It's a very important law for currents, potential, resistance, and finally circuits. If I have a battery, I have a wire connected through it, or a resistor. We'll have a resistance R. The current will be generated plus to minus. If I increase the battery power, current will be increasing. If I increase the resistance, current will be decreasing. That's what Ohm's law says simply. Current is equal to delta V, potential difference, or voltage over R. We can have different versions of Ohm's law. This is Ohm's law here. And we can write it in this version as well. Resistance will be delta V over I, or potential difference is equal to I times R. These nice figures are comparing the current with different setups where we change either the battery power or the type of the wire we're using. It changes the resistance. For example, here we have one battery. Assuming the same type of wire and same length, I'll just say same wire. I'm adding two batteries. I'm increasing delta V. So if we call this delta V1, this current one, call this delta V2, this current 2, current 2 is larger than current 1 because delta V2 is larger than delta V1. Go ahead and review all the rest. In the second one, delta V's are the same, but we have different wires. This is a thicker and shorter wire. It will have a different resistance than this wire here. It's a thinner and longer wire. Here we assume we have the same resistances, right? Because the same wire. Thinking in terms of R is equal to rho L over A. I have the same type of wire, copper wire, let's say. if the length increases, resistance increases, which is what happens here in the second case, very long wire. And if A decreases, resistance also increases, so double increase here. R2 is significantly bigger than R1. If the resistance is larger and potential differences are the same, then we can easily say from this version of Ohm's law that high resistance, low currents. If I call these currents I1, I2 again, I1 is larger than I2. I can also safely say significantly larger because resistance is significantly smaller. Inverse proportional to R and I. Go ahead and try this one. It's a simpler version. We have different materials now, copper and iron. All you have to do is check their resistivities. Rho is equal to R is equal to rho L over A. Same L, same A. Whoever has a higher resistance, which I believe should be iron, will have a higher resistance. Whichever has a higher resistivity will have a higher resistance, and you will decide what will happen to current accordingly because they have the same potential differences. So go ahead and check that and compare I1 and I2. Ohm's law tells us that if we have a plot of current versus potential difference or voltage, we'll have a straight line. And if we look at the tangent of that straight line, that's the slope, by the way, right? Slope of that line is always equal to rise over run. Rise here is I, run here is delta V, so that's I over delta V. Now going back to Ohm's law, I is equal to delta V over R. I can solve for R, switch in positions, and inverse multiplication always possible. R will be equal to delta V over I. So the slope is inverse of R. And I can solve for resistance. Same goes for if I have potential difference versus current, right? I'll also have a straight line. I could have delta V here, current there. That also will be a straight line. And this time, slope, this time slope will be equal to R. Because rise now is delta V and run is I, so delta V over I will have R. So if you're given a graph, go ahead and use the slope to get to the resistance, which is what is asked in here. You will find the slope, inverse it, find the resistance. It will be 0.02 ohms. This question is about calculating the resistance using rho L over A. This lecture is already getting long. I'll skip this, maybe make another video to describe it. But overall, we are given a power. We're not at the point of learning about power yet. We won't be needing that. But sometimes something is given, we don't need it. We are also given a resistance R, 240 ohms of this light bulb here. It will have a resistance because it has wire across. At the operating temperature of the tungsten filament, the resistivity is about 5 times 10 to minus 7 ohm times meter. We are given resistivity 5 times 10 to minus 7 ohms times meter. Unit of resistance is ohms. We use Greek letter omega for that, and resistivity is ohms times ohms times meters. If the wire used to make the filament is 0.04 millimeter in diameter, so we know the diameter here. Right away we find the radius, 0.02 millimeter, convert to meter, find the area, and we're asked to find how long must the filament be if those are the case. So we're asked to find L, and we'll solve for that. Simply cross multiply, divide each side by rho, you'll have R times A over rho. Input, everything in, and solve for the length. Resistance and current and systems or simple circuits actually can be used in medicine a lot and are used in medicine a lot. This woman here is measuring her percentage body fat by gripping a device that passes a small current through her body and measuring the resistance, which gives the device a structure of her body and which can tell about the percentage of body fat. Another application is electrical impedance tomography. Again, a current passes through body and a resistance is measured towards the current. Blood is a better conductor in the body, so if it's a better conductor, its resistance will be low. Other parts are higher conductors, so they map the area of a body. For example, here the chest, lungs will have high resistance, heart will have low resistance because of the blood with the low resistance. And it is mapped. Red here is showing low resistance. High resistance, and so on. So when you color code the section of a body, you can understand if there's any problems with the circulatory system, if the resistance is not as low as is expected, and so on. That means there's some maybe a clog or so on. It is easily can be found. Alright, I'll leave it at this part. Another problem very similar to the one I discussed, I'll skip that, and I'll see you in the next lecture.